Tutor, where school is made simple. Let's go.
In this video, we're going to look at the rules of exponential expressions. There are 9 of these rules, so I apologize in advance because this video is going to run longer than our normal videos. We start by looking at the first rule, which describes how to handle two exponentials with the same base but different exponents being multiplied times each other. So our rule is that b to the n times b to the m is equal to b to the n plus m. As an example, I'm going to use x cubed times x to the fourth, which according to the rule would be x to the 3 plus 4, or x to the 7. I'm going to then expand x cubed and x to the fourth and substitute into the previous equation. So then I get 3x's times 4x's. So I would then have 7x's, which is x to the 7th, confirming the rule. Similarly, when I have two exponentials with the same base dividing, I subtract the exponents. I subtract the bottom exponent from the top exponent. So that, for example, I had x to the fourth over x cubed, then that would simplify to x to the 4 minus 3, which is x to the 1, or x. I'm going to use the same logic as before by first expanding x cubed and x to the fourth and then substituting into this equation. So I get x to the fourth is xxxxx over x cubed xxx, and then I separate each of the fractions to take advantage of the fact that x over x is equal to 1. I can then cancel out each of these fractions, which would leave me with 1 times 1 times 1 times x, which is simply x, which confirms my rule. When I have an exponential itself raised to an exponent, the rule says that I should multiply the two exponents. Keep the same base and multiply the two exponents. So let's look at it when I have x cubed raised to the 4th power. That would be x to the 3 times 4, or x to the 12th. So again, we're going to expand x cubed and then substitute it into our original formula and get x cubed to the 4th, which is equal to xxx raised to the 4th. So that means xxx times itself 4 times. This results in 12x's, hence x to the 12th, which confirms my rule. Now we're going to do this a little bit differently. We're going to look at where the exponent is now the same, but the bases are different, and we're multiplying them. The rule says that we would keep the exponent the same outside, and then inside the parentheses multiply the two bases. So let's look at it using x cubed and y cubed. Our similar exponent is the cube. So according to the rule, this would be x times y raised to the 3rd power. So again, I'm going to use my expansion and see that x cubed is xxx, y cubed is yyy. Put them together, I have 3x's, 3y's, and then I'm going to rearrange them according to the associative property. And then split up the multiplication and see that I have 3 sets of xy, which is the definition of xy parentheses cubed. Notice that as we go through this, these rules, while seemingly complex, are actually very simple to see in action. And the hope is that by seeing this in action, you can go back and recreate this when you need to use them. So let's continue on with Rule 5, which is going to be analogous to Rule 2. The difference here is that now I have the same exponent but different bases. So that when I divide two exponents with the same exponent, I will bring the exponent outside and keep the bases inside as a fraction. For example, x cubed over y cubed, according to the rule, would become x over y cubed. So let's go back to our expansions and look at x cubed over y cubed as being xxx over yyyy which I'm then going to simplify into three separate fractions, x over y, which is the definition of a cube. It's x over y 3 times. So it'd be x over y cubed. Now we're going to depart a little bit and look at a slightly different approach. I think we can all agree that b to the fourth is b times b times b times b. Similarly, b cubed is going to be b times b times b. And I know this from looking at rule 2, because 3 is 4 minus 1, which I can then represent as b to the 4 over b, which gives me 3 b's. Using the same logic, I can say that b squared will become b times b, and b to the 1 would simply be b. Therefore, b to the 1 is b, and this is true for all bases not equal to 0. And now, how do we take it one step further to get to b to the 0? How do we know that b to the 0 is equal to 1? We're going to use the same logic as before and say that b to the 0 is really b to the 1 divided by b, because that's all I've done in each step. And b divided by b is 1. Therefore, b to the 0 equals 1. And if b to the 0 equals 1, then what does b to the negative 1 equal to? Well, first I can say that negative 1 is 0 minus 1. And once I know that, then I can come back to rule 2, which has b to the n over b to the m equals b to the n minus m. So I simply take it in reverse. I have the n minus m, so now I have to split it up into a fraction, which would be b to the 0 over b to the 1, which would be 1 over b. Moving along, b to the negative 2 would be b to the 0 minus 2, or 1 over b squared. And b to the negative n is going to be b to the 0 minus n, which works out to 1 over b to the n. This is probably the most difficult of the 9 exponential rules to explain simply. To do it, I go back to the concept that 4 cubed is 4 to the 3 times 1, or 4 times 4 times 4, the key being the times, the multiplication. When I look at 64 to the 1/3 power, which is what I'm looking at, really fractional exponents, well, 1/3 is just 1 divided by 3. So 64 to the 1/3 means 64 divided by a base 3 times will equal to 1. So moving forward with this, the goal is to find out which number divides into 64 perfectly 3 times. Some of you may know the answer already. It's 4. So that I can say that 4 cubed is 64, and then in reverse, that the cube root of 64 is going to be 4. And this is how we have the connection between the fractional exponent and the root.